Alright, so now we will solve question 2. So let's read the question at first. So the question is the wall OAB of the water container shown is pivoted about O. So it is pivoted here. Determine the moment about O due to the force of the water on the wall. So here is the water. If you see, this is the container. This is the free surface. I say earlier this symbol calls the free surface. So this water, you see, we need to calculate the moment about O due to the force of water on this wall OAB. This wall is 4 meters long in the direction into the base, and the other dimensions we know from here to here, that means A to B, it is equal to, okay, so this is 2, and this C, this distance, this is 1, or the distance from this, this all the vertical distance. If you draw a vertical projections like this, so the vertical projections and this distance, it is also 1, be equal 1. So let me draw this on, maybe just redraw a little like this, and then it will help us to solve this question. So if we redraw this on like this, so this is the wall OAB, and this distance is given, this is 2 meter, and this distance is given 1 meter. So up to like this distance. So I'm not joining this, and then it may mislead you. So we say, okay, this distance is 1, this is 2, and this is 1 given like this distance. What we did here is we just draw a vertical projection. So this wall is OAB. Water is, applying some sort of force on this wall. So we just developed a vertical projections of this wall OAB. So the vertical projections of this wall means it will be like this to this point. So this is an imaginary section. So what I said is, let's say this line is dotted, and the other, this is the solid, this is the real wall OAB, and we developed the vertical projections of the wall OC. Let's say this is actually OC. If you see this design, we just developed a line like this. Okay, so this is OC. So now if you look here, this all OAB, this is not a the straight, the flat surface. This is you can see the change of the directions from here. So consider this is a curved surface. Okay, this is a curved surface, and this is the water. So if you can remember, we solved the first question and we discussed the theories. So when it is the curved surface, then we need to think about the force about different directions, because with the change of the directions, the force will be different. That we discussed in detail in the theories. So here, two different force we like the horizontal force and the vertical force, because this is the theory we know. When it is the curved surface, if we took a very small section like this, so let's say the force always acts through the vertical way, like the perpendicular way. So this is perpendicular, it will create some sort of angle 90 degree. So if we want to get this force, we can divide this force into two different types of force. Like one is the horizontal force, the other is the vertical force, and the sum of this force is this is the resultant force. So we discussed this on earlier. So in this case, this is a curved surface, so we will have the horizontal force and the vertical force. So we will calculate the horizontal force at first, and then look at the question. Actually, we need to calculate the moment. So the moment, it is equal the force, the horizontal force, and the corresponding distance plus the vertical force and the corresponding vertical distance. So that's actually we know the theory how to calculate the moment. So if we can to calculate the moment about this point O, we need to calculate the horizontal force, the corresponding distance, vertical force, and corresponding distance. So let's calculate the horizontal force at first. So the horizontal force here, it will be the force on the vertical projection of OAB. So definitely the horizontal force, if we say this is the vertical projections, so we can say maybe this is the centroid, maybe this is the center of pressure. Okay, we can say it is CP or HC. Okay, just put say anything, any values. You can define whatever you want. So let's say this is C and this is CP, the center of this is centroid, this is the center of pressure. Center of pressure will always be below of the centroid. You all know the vertical force, sorry, the horizontal force will go through this way to the the center of pressure. So that's the, and definitely what we know from this formula is when it is the curved surface, the force will always act through the the perpendicular directions and onto the base. So that means the horizontal force will act on the vertical projections of this wall. So we develop these vertical projections, which is OC. So that what I said here. The horizontal force, it is equal the force on vertical projections of OB, which is actually OC. So when it is the force, horizontal force, this is the pressure and the area, the corresponding area. Now we need to think about this height C. Look here, guys. This height C. We know rho, we know the gravity, this is only body force that we said, and the area is okay, we'll discuss the area later, but why the height C equal 3/2? You always know that, like me, I just wrote it here. So length of the CO, that means that vertical projection. So we had the wall is like this, and we developed a vertical projections like this. So the center of pressure is definitely, it is centroid is just the hub, isn't it? So it was O and it was C. So this total distance, it was 3. How it was 3? Look here, it will be clear. So this distance is 2, this is 1. So 2 plus 1 is 3. So that means this length is 3. So the centroid, it will be just the middle. Okay, so that means 3/2. So there's, I said here, the length CO is 3. So centroid will be 3/2, which is the height C. And the other thing is this length from here to here, it is given 4. It is given 4 from here to here. But this vertical projection distance is 3. So height is 3/2, and when it is the area, so these vertical projections into the length. So length is 4, and we know this vertical projection is 3. So we got the horizontal force is 176,400 Newton. Now the other important thing is once you want to calculate the moment, then the other important thing is when you have the force, then you need to calculate the location of the force. So we got the force magnitude, and now we will calculate the location. So from the theories, we know the location, the LCP, okay, the center of pressure location along the horizontal surface. It is the LC plus IC LCA. This is the the second moment of inertia. I believe that if you went through the lecture slides and through the books, then you already have this understanding. Unfortunately, we can't drive this expression. This is you will get from your book actually how to get this locations of this formula. But I'm not just discussing this on here, but you will get this formula from the book. So the length L, let's say L is actually here height. We will calculate the moment. So what we are telling is, let's say the L equal haze. Here we see LCP equal LC and IC LCA. So just let's say L equal haze, then it should be the haze CP, that means the distance of the center of pressure. This is the haze C centroid, okay, the centroid distance IC, okay, that's the second moment of inertia, and A is the area. So from the formula from the book, we know that actually IC for a rectangle, when it is a rectangle, this is b haze cube over 12. Let me show you the slide that I prepared for the tutorials. When yeah, you see, let me show this one at first. So it is b haze cube 12. So let's see the formula here. When it is a rectangle, then you see this IC equal a b cube over 12. They just use different variable, that's it. So that's the only difference. Area equal AB, and this is the inertia formula AB cube 12. Here we said it is B haze cube over 12. That's the same thing. So haze is actually, so we know this one. So now substitute this value. Haze CP equal haze C plus B haze cube over 12 and haze CA. If you substitute all the values haze C, this the centroid distance, that means the centroid distance is 3 over 2. So which is 3 over 2 because the total length, the vertical projection, it was 3, so 3 over 2. And the B, this is the length, okay, B is the length of the wall OAB. It was given 4, so it was something like this. So this length was 4. And haze, we know, the haze. Here you see it is the haze cube is 12. So the haze, it is equal 3. This is the height 3, and haze C, it is over 12. So it is over 12, and then haze C equal 3 by 2, and the area is this 4 and this 3. So this is the haze CP. That means the distance from the the center of pressure, haze CP. That means let me go back there, and okay, before going to that point, here you got haze CP equal 2 meter. That means the height from up to the center of pressure. CP is the center of pressure. So if we say this is the centroid, it is the center of pressure CP, and it is the O. This total length is 3. Okay, this total length is 3 meter. This total length 3 meter. We calculated CP up to this distance. So this is 2 meter. So this is 2 meters. So that means the distance from this O, that means the horizontal force is acting through this way. Let me use different color, then you will get some better understanding. So the horizontal force is acting through the center of pressure. If we want to calculate the moment here, we need this distance. So we got the center of pressure distance is 2 meter. So the total distance is 3. So if we subtract this value, 3 minus 2, that means this 1 meter is the distance from here to this horizontal force distance. Okay, so that value we actually need when we will calculate the moment about this point O. So this is actually the distance. So let me tell again, we know this formula, haze CP equal haze C and IC haze CA. So IC, the moment of inertia, for rectangle, we know from the theories it is B haze cube over 12. We substitute the values, then we substitute all values. It is 2 meter. So we got the center of pressure distance 2 meter. And now we need the moment about this point O. So we know the moment formula is the horizontal force and plus into the distance, the force into distance. So if we want to calculate the moment at this point O, so we need this force and this distance OP. So we got HCP equal 2 meter, and this total length is 3 meter. So if we subtract this value from 3 minus 2, then we will get the distance from here to here. Okay, I believe now I got some sort of understanding. So now we have done with the horizontal force. Now the vertical force. This is really important, guys. So when we will calculate the vertical force, let's see this one here. What we did here is we just make a small divisions. So it was like this. If we draw a line like this way, then it will be a rectangle, it will be a triangle. So the first thing is, if we actually want to draw the the centroid, so let's say in this case, actually what you can do is, maybe if you just draw a line like this, if you draw another line like this, so this point, it is, let's say this is the centroid for this one. When it is the triangle, so let's say this, draw this line, and let's draw this line, so this is the centroid G2. So for this rectangle up to this point, that means the distance from this all to this centroid, let's say from here to here, this distance is x1. Okay, that's this distance is x1. When it is for this triangle, so then this distance is from here to here, this is x2, this is x2. And I will just remove this two line for better understanding. So here you see we got this centroid by using this diagonal. So this distance is x1, this distance is x2. And now if we consider the whole object, so let's say so the centroid may be here, because of this triangle. Let's say it was initially for this rectangle here, so let's say this distance is here x1, this point, this is the centroid for this whole domain, and this distance is x. Actually, vertical force, you all know the vertical force will act this way, isn't it? So vertical force will act like this way, and then we need the distance. If we want to calculate the moment, then we need the corresponding distance. Okay, so here what we did, we just make two different on triangle, on rectangle we calculated the center of gravity and the corresponding distance. We define x1, x2, x. So now if we want to calculate the vertical force, so you all know the vertical force is actually the density, okay, density of the material, gravity, and the volume where the force is actually acting, domain, the volume of the domain. So here, in other words, the vertical force is equal to the weight actually, which is acting to the downward directions. So here we says the vertical force is the weight of this domain OABCDO or OABCO. So you say the weight of OABCO acting through the centroid. What is the centroid for OABCO? This centroid is this point, and the distance is x. Okay, maybe we can see this figure here. So this is the centroid for this rectangle, this G2 is the for this rectangle, and this is for this whole domain. So now the weight, we will calculate the weight of the ABCD. So before calculating that, we know the weight is equal rho g and the volume. So let's calculate the volume of this OABCO. So the volume is, the formula is 4 into the area of this. So we don't know the area of this, this geometry, but what we did, we considered this is a rectangle, this is a triangle, and we know the area for this rectangle and triangle. So that's why we said area of rectangle and area of triangle. Right. So the area of rectangle ABCD, it will be AB and BC. So you see AB and BC. This AB, BC, and it is 2 and 1. Where it is triangle, we know the formula. It is half into this vertical and this, this basement DO. So AD and DO. This base and this vertical on. So it is half into AD and DO. So all of this, if this on is 1, it will be 1. Okay. because this is a rectangle. So this, if it is 1, this is 1. If it is 2, this is 2. So similarly, if this one is 1, it will be 1. It is given there in the design. So it will also be the 1. So we got it is 1 and 1. So AB equal to, and rest of 1. So we got it is 10 meter cube, the volume. Now if we want to calculate the weight, so I told you earlier, weight, we solved this sort of questions earlier. If the mass is given, then it will be mass, gravity, and the volume. Here we will consider the density. So the density, rho, gravity we know, and the volume we know. So we got the weight. Alright, so we are almost done with the problem. We got the weight, and now we will calculate the locations, the value of this x, okay, this distance, the value of this distance. So to determine the horizontal locations of this centroid, what I discussed earlier, we break this design into a rectangle and a triangle. We design, this is the centroid G1, this is the G2, and this is for the overall one. So if we calculate the values for x1, x2, so the x1, eventually when it is the rectangle, it should be actually like here, it should be somewhere here. So it is, you see, if you say generally this is the half of the this A's, this CV. So we can say actually x1, this distance is half of this CB or BC. So let's say CB. So it is half, and CV, it is equal 1, so it is 0.5. When it is the triangle, you can say it is more or less somewhere here. So let's say this is the first part, this is the second part, and third part. So this distance x2, it is actually the 1/3 of this AD, which is 0.33. So you see here, what I said, this is the x2. So if you can see, you can create one more section here, so it should be just 1/3 of this AD. So that means we got x1 and x2. We actually need x. So now if we need this distance x, so we can write it like this: the x for this whole domain O, A, B, C, D, O into the area of this domain equal, we can say, the distance x1 and the area of this plus the x2 and OAD. Look, I'm telling again, our ultimate target is we actually want to calculate this x. So we said the x, this distance into the area of this whole domain, is equal to just the distance x1 into this area plus this distance x2 plus this area OAD. So when it is the area of ABCD, then it is actually 1 into 2. Area of ABCD, that means it is 1 into 2, that we did earlier. So an x1 equal 0.5, so it is 0.5 into 1 into 2. When plus x2 equal 0.333, and the area of this triangle is half into 1 into 1, okay, over the area of A, O, B, C, D, O. So that means this one again, this 1 into 2 plus half of 1 into 1, the area of OABCU, that means this one plus this one. So by using this calculation, you see we got the distance x, that we actually need this one, it is 0.461. So once we have this, that means now we have everything. We have the vertical force, we have the distance, we have the horizontal force, we have the distance. So once we have this, then we can calculate the moment. And the moment is the horizontal vertical force and the this horizontal distance, the horizontal force and the vertical distance of this. So you see the moment at O is F is the horizontal force, the distance, vertical force, distance. We have all of these values, so we got the moment. So that's all. We have done with the solution. So the main tricky part was actually we need to calculate the the distance and the force, the horizontal and the vertical force. So here you see what we did. It is a complex design, so we make it simple. We just make it as a rectangle and a triangle. Then we calculated the distance. We created the the centroid, and usually I showed you how I did it. In the rectangle you need to use the diagonal, and when it's the triangle you need to use this diagonal, and then you will get that centroid. So we got the distance by using the formula, and we got the moment. So that's it.